All right.
Good afternoon, everyone. So our group has worked on like a fully integrated adaptive CMOS neuromorphic controller for energy efficient cardiac pacing, and our group consists of Austin, Alexander, Deepta, and me, Vivas. So next slide. So yeah, like how does a typical nerve heart works? So there's like uh, nerve fibers called the SA node, which is the where the initial signal input comes, and the SNOD is at place at the right atrium in the topmost part, and there it connects to the AV node, the atrioventricular node, through like three fibers, and from there it's like the connections goes towards the atrium and like towards the ventricles. For with like there's the bundle of His, there's the left and the right bundle branches, and then comes the Purkinje fibers, which release the signal towards all the heart muscles, and that leads to like the initial ventricular contraction, which can be seen in the R wave in the signal down in the ECG, and with the typical normal heart rate that comes, it's around 60 to 100 beats per minute, or that's like 1 to 1.6 hertz. And next slide. So yeah, like how the spacing between the intervals within the 2 hour waves, it's like indicates the ventricular depolarizations, and that's the primary input to detect abnormalities. So in cases like in bradycardia, there it's like the peak higher interval, it increases towards 1200 to 1500 milliseconds, and these causes like the SA node dysfunction, the AV block, or like it can be due to age and ischemia. And the consequences, it can be like dizziness, fatigue, syncope, and there is risk of cardiac arrest as well. So yeah.
So the system architecture. So we start first. I'll start with the heart where we do a heart rate measure. We simulate in Canvas, and then in the second part we had a silicon coil that includes a bandpass filter plus a rectifier plus a low pass filter, and then the PMOS to change from voltage to current. The second part here is to extract the temporal rhythm features. The input is from the ECG and the output is a frequency band signals with the spikes. And then lastly, we enter into a pulse generator. This delivers a pacing pulse. The input is the trigger, and then the output will be the R wave simulates that goes back into the heart. In this slide here, we wanted to try to simulate a heart the um the heart as close as possible. So on the top here is like a normal heart where we use a piecewise linear voltage source to simulate it. And then for the bicardiac heart, we also included a little delay between each one to simulate this bicardiac heart.
So for the design of the bandpass filter, we are wanted to select for the desired heart rate range. So in the case of resting heart rate, as Vivas mentioned previously, it's around 1 to 1.6 hertz, but we wanted to allow the heart to also speed up. So for situations when the patient is exercising or otherwise actually does want a higher heart rate to deliver oxygen faster, we wanted to allow it up to a certain threshold level that is still not tachycardic, but allows them to have an increased heart rate. And so our desired band, thus becomes 1 to 3.5 hertz, and it allows us to get our transfer function and attempt to program our bandpass filter to select for that frequency. And so the center frequency here would be the geometric mean between our 1 to 3.5 hertz, which is around 3.7417 pi. And then we also wanted to add in a small gain factor to get that transfer function, the whole region desired region of our band above unity gain. And so here's what that looks like in Bode diagram form, where we have our whole band there from 1 hertz to 3.5 hertz above there, and our quality factor of 10 is making that peak much more selective toward our band because we really need a narrow band for that very, very small reach we want to select for. And here we also don't really care about phase because if we're pacing faster than the heart is in bradycardic tendencies, then at some point the pacing from the pacemaker will override the natural pacing from the heart and continue to override it as it's pacing before the heart can pace. And so here is our cadence diagram of the silicon cochlea. This is the interior of the symbol here. So we have our two bandpass filters in sequence, then the rectifier, and then a low pass filter at the other end. And then since the input impedance to our bandpass filters is infinite because it just pipes to the gate of a transistor, we had to add in some sections to allow basically the current to pass for back and forth, so we wouldn't have floating voltage issues. And so here's some of the results of testing the silicon cochlea in particular. It wasn't working with the natural heart signal that we were simulating for a number of reasons. Namely, the first one, namely being that the natural heart signal actually passes outside of our rails, and so the signal would start to get clipped there. And it's also comprised of multiple different sort of base fundamental frequencies and harmonics. And so it wasn't necessarily able to pick up on the frequency that we wanted, which is that of the the heart's. I mean, any particular wave, but that from any particular wave to any particular wave. So like Q wave to Q wave, T wave to T wave, or R wave to R wave. Um, and so we tried to test it with just an AC signal to uh, debug why it wasn't working, and it sort of resulted in some very interesting situations here where the bandpass filter is showing some pretty severe floating voltage issues among other issues. And by the time it gets to the rectifier, it completely breaks down. You know, we've lost the majority of the amplitude of our signal, and it's strictly DC at this point, which I mean the rectifier technically is supposed to do, but it's not. It doesn't maintain the spikiness that you would expect from the rectifier at this point. So not sure why that's happening, but it's definitely room for improvement. And then here are some of the other tests with the actual natural heart frequency, where we're seeing that same sort of voltage creep coming from somewhere within the circuit. Um, and of course, that basically just leads to a large if we can't select for that output, then we have to select for one side of the differential outputs. But then when it comes with such a large DC offset that it basically just drives the pulse generator at the same frequency no matter what. And none of that signal actually matters because it's dominated by the DC offset. And then so here we have the pulse generator. This one actually worked flawlessly, and it's an augmented form of the action potential silicon neuron that we saw in homework one. Um, and Austin will tell you more about it.
Yes. So here, this is the pulse generator layout that Alex has built with a BR and BA pins to capacitors, and then the BM pin to output and a capacitor. Here's another pulse generator simulation. This purple one is a normal heartbeat, while we also included a sine voltage source that pulsed at a frequency that's close to where the heart goes to the highest peak. And overlaid the strong green is the pulse generator. As and these are the design values.
So this is the direction that we were trying to work towards of being able to have this kind of simulation, but we still haven't been able to get our silicon cochlea to work to that stage. So hopefully with your suggestions, we can figure that out. But we are thinking that the things to improve on would be to downstep the high voltage signal to a lower voltage range, as Alex was mentioning. So it doesn't hit the rails when we do our logic processing on it. And also possibly optimizing the low pass filter for the heart rate rather than just using what we were using for the silicon cochlea for a regular sine wave. Once we're able to get this to work, um, hopefully the eventual future possibilities of this project would be one real-time adaptation, which would help continuously track physiological rhythms like stress, movement, or breathing. And instead of using fixed thresholds, an adaptive system would adjust pacing automatically as the body's need would change. This would prevent under or over pacing. And then having a neuromorphic design would um, replicate biological timing with very low energy consumption. So the power needed and increasing the lifetime of the implant and reducing the need for battery replacement surgeries would be a benefit. Also, the technology, incorporating the technology art or adaptive resonance theory would um, combined with some analog memory elements could allow the pacemaker to learn long-term patterns in the patient's heart cardiac behavior. So this would enable more stable learning without catastrophic forgetting. So it would be able to change itself over time while keeping older patterns intact. And this would make the device more personalized as the patient ages. And this figure on the right is a paper that we found was that did have a neuromorphic design that uh, could possibly show how future pacemakers could have um, more naturalistic and adaptive pacing. We'd like to know your thoughts on how we can improve our silicon cochlea. Thank you.
Thank you.
Thoughts, guys.